In this video, we're going to talk about active transport. And so this active transport is very important for making gradients. And as we know, gradients are very important to cells. We talked about how gradients are really important in terms of a sodium gradient and a potassium gradient. And the sodium gradient's needed so that when an action potential goes down the neuron, the sodium channels open up, the voltage-gated channels that is, sodium floods in, and that depolarizes the membrane. And then potassium channels open up, potassium floods out and repolarizes it. And if there weren't any gradients, that action potential would not be possible, and basically our neurons would not work. In fact, that's one of the ways that anesthetics work. They basically prevent the action potential by either preventing the gradients or preventing the channels from opening up and so forth. So if you don't have these gradients, you're going to have major issues. So how do cells make and maintain those gradients? All right, that's what we're talking about. And what do those gradients get used for? And we've already seen that again with the neurons. So think about this for a second. Which one of these processes is moving a product against its natural gradient? So we have this first part here, 2, 3, or 4. Which one is moving a product against its natural gradient? In other words, moving it from low to high, because its natural movement would be high to low. Well, the answer to that would be this. And how do we know that? Well, one, it says active. Active transport, by definition, is moving something actively from low to high. So it takes energy, it takes effort to do that. And that energy is shown right here. So this is the one that's using ATP in energy. And so the reason it would be using energy is because it's moving something from low to high. Diffusion happens from high to low. And remember, we have passive diffusion and we have facilitated diffusion. So this would be the passive diffusion, and these would be facilitated. So I'm going to get rid of that word passive there and turn it to diffusion. But all of these are still moving something from high to low. The only way to move something from low to high is with energy. That's active transport. So what is the source of the energy for this? Well, we already saw ATP. So ATP is a common energy source used for a lot of different things. Plants can use light. All right, so during the light-dependent reactions of photosynthesis, light is used to create high-energy electrons, and then those high-energy electrons are used to create that proton gradient that basically is used to make ATP and ultimately the energy used to make glucose. So plants can use light. And then the other thing is coupled transport. All right, so this is using the energy of one thing moving from high to low. All right, so let's say these are moving high to low. Well, we know that moving from high to low gives off energy, and that energy can be used to move something else from low to high. So coupled transport is when one thing moves from high to low, and that gives off energy, and that energy is used to move something else from low to high. So coupled transport basically has to be a either a symporter or an antiporter. It can move things the same direction, opposite directions, but it's moving two things at once, one from high to low, for the energy to move the other one from low to high. So here is our sodium-potassium exchanger. And in our neurons, we know that our sodium-potassium exchanger, so if this is the membrane of a neuron, so this is the inside of the neuron, we know that we have our sodium-potassium exchangers, and it is going to take 3 sodium and move them back outside, and it's going to take 2 potassium and move them back inside. And these are going from low to high. This is to reestablish that neuron's gradient. So if it's going from low to high, it's going to require ATP as energy. And so this is how this works. The transporter opens up to one side. Sodium basically starts to flow in and bind, and there's 3 binding spots for sodium. Then ATP basically gets used, and that phosphorylates this right here. So there's the ATP going to ADP, that's the energy usage. And then this causes the conformation change, which allows it to open up to the outside, and now our sodium, our 3-sodium, is released to the outside. While this is exposed to the outside, it now has the potassium binding sites, so potassium, 2 of them, come in and bind. And that binding is enough to cause a conformation change to open to the inside, so our 2 potassium have come in. And then sodium will bind, and then the ATP will do its thing, and basically this cycles around, allowing this to kind of repeat over and over again. But each time it does this, each time it moves 3 sodium out and 2 potassium in, it takes 1 ATP. So there's your active transport use of energy to make that gradient. So one of the things that this can be used for also is coupled transport. So let's take a look at this. So with your intestines, especially the intestinal cells that are towards the end, our body is very good at pulling in all the glucose it can from our food, right? So there's actually going to be higher levels of glucose inside the cell than inside the intestine lumen. So that glucose level is low. So if we're still trying to pull in more glucose to send it onto our bloodstream, we need to be able to move the glucose from low to high. We need to import it into the cell where its concentration is already higher. We know that's active transport. It's going to take energy. Well, it uses coupled transport. The energy moving sodium from high to low is used to move the glucose from low to high. So here we have that. So we have high sodium inside the, it's supposed to be an N, sorry, inside the intestine lumen, and we have low sodium inside the intestine cell. All right. So in here, the sodium, let me pull up blue here, the sodium is low inside and the sodium is high outside. And so when sodium moves from high to low, moving in, that is a symporter pulling glucose from low to high. That is coupled transport. The energy from sodium moving from high to low is coupled to power the movement of glucose from low to high. Right? But obviously this can't happen forever. If this was the end of the story, eventually all of our sodium gradient is lost because we're pulling a lot of sodium into the intestine cell in order to power the glucose movement. So in order to maintain that gradient, we have to pump the sodium back out. So there are sodium-potassium pumps, and there would actually be some on this side as well. There are sodium-potassium pumps moving the sodium back out. All right, moving the sodium back out, and by doing that, it maintains the low concentration of sodium inside. This is where the ATP comes in. So coupled transport still is going to need energy in the form of ATP ultimately. It's just that that ATP is used to create the gradient. The ATP is used to create the sodium gradient, and then the sodium gradient is used to drive glucose. So no sodium gradient, if you didn't have a sodium gradient, you wouldn't have glucose import. Right. Last thing I want to talk about is regulating pH. I apologize that the import of this slide kind of got over a little bit, but pH is really important to regulate, and so there are membrane transporters, active transporters, whose job it is to move protons and or sodium HCO3. So let's think about this for a second. Obviously, if we moved a proton, you're going to directly affect the pH. But you can also import NaHCO3. So if we import NaHCO3, if we make this get higher, what's that going to do to the concentration of protons? Well, it's going to shift our equilibrium over a little bit. And so in order to make H2O and CO2, that's going to ultimately mean the proton levels have gone down, and that's going to it's going to make the cell less acidic. It's going to bring the pH up by lowering the hydrogen ions. So we have a sodium and HCO3 exchanger. So this sodium H3O exchanger basically takes HCl out, and by taking HCl, you've basically removed a proton from the inside of the cell. So this is the cytosol, and this is the extracellular. And at the same time, it pulls a sodium HCO3 in. So here we've reduced the amount of protons inside our cell by pumping protons out, and we actually have shifted this equilibrium to the right by bringing the HCO3 in. So this basically is going to help increase the pH inside the cell. This is one of the ways that we make sure the cell doesn't get too acidic. But again, it's this coupled exchanger. And sodium, we already know sodium has a high concentration outside the cell. So when this gets pulled in as sodium HCO3, that gives off energy because it's going from high to low. And in giving off energy, it drives our protons from low to high, and that's how our pH can become regulated. All right, thanks. Hopefully this all makes sense. Let me know if you have questions, as always.